Hi guys, we are going to be talking about intermolecular forces. So by now you should know what a polar molecule is, and you should know how to determine the differences between electronegativity. Now, um, intermolecular forces is the forces that happen between different molecules. Okay, so the force between this molecule and that molecule right here. So we're not talking about the intramolecular forces, meaning the forces in between the two atoms. Okay, so easy way to remember is intranet is the school's internet where you can store your files and everything is inside the school. So intra, where internet is international, worldwide, all very in between two different places. Okay, so that's just the way I remember it. So intramolecular forces within the same molecule. So the forces that go to play right here inside the molecule. All right. So indicated by the blue arrows on your screen, you'll see those are your intramolecular forces. Think about it. Intermolecular forces, if we did not have the forces in between molecules, everything around us will be gases because you have different molecules that are exerting a force on each other. Okay, so everything that is a solid, there is a force between the two molecules. All right, so intermolecular forces dictate a lot of properties. They are weaker than covalent bonds because bonds are obviously stronger. It's holding the atoms together to make up a molecule. We also call all of these forces van der Waals forces. He's the guy who kind of came up with the idea that to say that, wait a minute, in between molecules there had to be forces. Okay, so the grouping of them can be called van der Waals forces. You cannot compare the forces of one kind of van der Waals force to another. Okay, so each of the different forces are unique. Okay, so let's take a look. There are 5 of them. Okay, so it's going to be dipole-dipole, induced dipole, see how my memory is, induced dipole, ion induced dipole, you get London dispersion forces and hydrogen bonding. And I'm sure there's one I'm forgetting, but anyways, there's 5 of them there. So let's see which one my memory is not helping me right now. So you get an attraction between one end of a polar molecule to another end. So it depends on the strength of the polarity. So if you have a very highly polar molecule, you're going to have a very high boiling point, because if you think about how strong or how highly polar the one side is, there's going to be an extra attraction towards another molecule. So the boiling point is going to be higher, breaking the forces in between the molecules will be harder, right? So dipole is a polar molecule. 2 ends of the poles of the molecule have different partial charges. So here's just a representation. So here you can see positive, negative, positive, negative. And so if you think about if these 2 forces, this is very highly positive, very highly negative, lots of electrons in this area. So for example, like fluorine combined with an oxygen, for just for an example's sake, very highly electronegative, you are going to have a hard time breaking these bonds, these intermolecular bonds apart. Okay, so these forces that are being exerted, so these molecules will all line up. Now, I'm not so fancy with a computer, but if I could show you that all of these would line up and orient themselves appropriately. Okay, but here I'm really good with arrows, so I can show you how they will line themselves up. Okay, so the next one is ion dipole forces, so force of attraction between an ion and a polar molecule. So we know that ionic compounds are soluble in water. How do we know that? Because I know salt dissolves in water. Salt is NaCl, ionic compound, it dissolves in water. Why does that happen? Well, we have water, which is a highly polar molecule, one very highly negative side, one very positive, and then we throw in a sodium and we throw in a chloride. So why do they dissolve? Well, ionic bonds are pretty strong. However, when I throw in a polar molecule, this negative from the oxygen is going to have an attraction to a sodium. Okay, so and here my chlorine is going to be very highly attracted to my hydrogen. Okay, so here all of these ions will then be pulled apart into solution because of this polar water molecule. All right. So nonpolar molecules can become dipoles, for example, when an ion nears a molecule. Okay, so if I bring this ion here, little electrons, so you're going to pull all of those electrons closer. Okay, this is why they call it attraction. Couldn't resist. Anyway, love that cartoon. Let's take a look at another one, induced intermolecular forces. This is when a charge on a molecule causes a change in the distribution of charge on a nearby molecule. So induction means close by. Okay, so you would have heard about this term in grade 9 science, induction, and it's used for like photocopying in static electricity. So maybe you don't remember, but it is taught. So you get either an ion-induced dipole force. So you have a nonpolar molecule that distorts the electron density, and this nonpolar molecule all of a sudden becomes polar. So if you think about this nonpolar molecule, electrons are evenly spread, not quite, but anyways, evenly spread around these two, right? So somehow you have the sodium ion in the water, or sodium ion in solution. These electron that what were once, let's just go back, can I go back? Were once just evenly distributed are now affected by the sodium. Okay, so you have the electrons being attracted by that sodium. So now you're causing this unequal distribution of electrons, so now you're causing a dipole. That saying, you get an ion-induced dipole force. All right, so let's take a look what would happen if you had chlorine in the water or in the solution. You would have the opposite effect because now this forces the electrons to the opposite side. So this, again, an ion-induced dipole. So a dipole-induced dipole force, meaning you have a nonpolar molecule again, but you have this polar dipole molecule. It's going to cause a uneven distribution and distortion of charge. So the electrons are now going to be attracted to the hydrogen, and if the oxygen came close, it's going to repel the electrons and they will go to the opposite side, causing a dipole. All right, so London dispersion forces. So here I want you to think about, close your eyes, think about a long chain of molecule. You have all these electrons that are orbiting, circling around the atoms, and they're constantly vibrating. So even in polar molecules, this can shift a charge and make it slightly polar. Okay, so random, ongoing, depending on what the situation is. Okay, so as one molecule randomly becomes slightly polar, it affects the whole entire molecule. All right. So these random forces of attraction are called London dispersion forces. So it depends on the number of electrons in the molecule and the shape of the molecule. The longer or larger the molecule is, the more vibration. So you have a greater chance of these distortions that could happen. However, if you have a circular molecule, and if we talk about this in organic chemistry, that's grade 12, you will have less of a distortion because of it's a circle. Those charges can be easily spread over that molecule. So everything else being equal, the more greater the electrons, the higher the boiling point. Okay, so you will have this sudden distortion of charge caused by some friction, okay, and causing this dipole. And this is called London dispersion forces. So now you will have this attraction between two molecules. All right, hydrogen bonding. So this is where hydrogen is bonded to a highly electronegative atom. Okay, hydrogen to oxygen. Remember these three. Highlight this, underline it, star it, score it, I don't know, something. You need to remember this. Highly electronegative, fluorine, nitrogen, and oxygen. So you have this lone pair of electrons on these highly electronegative electrons. They in themselves cause dipoles. Okay, so let's take a look at hydrogen bonding in action. So it happens when you look at water, for example. You have all these forces in this water molecule. You have this lone pair, you also have this positive hydrogen. What happens? When you have it as ice, ice floats. We know that the density of ice is lower than that of the liquid because ice floats. Why does that happen? Is because water molecules will orient themselves in a hexagonal pattern, just like that. So you will have, that's why snowflakes are that beautiful, all those beautiful shapes, because it's the water molecules themselves will orient themselves in this hexagonal pattern. Okay, so you can trap molecules in a hexagon, so it takes up more space than in a liquid form, and that's why ice floats. So where are hydrogen bonds important? Hair and DNA. Okay, so in between the helix, what keeps the nucleotides attached to each other is the hydrogen bonds between them. Okay, and so in replication, you will have the breaking of these hydrogen bonds. Okay, so how do you determine polarity? Draw the Lewis structure, determine the bond polarity, draw the polarity arrows, put partial charges on the diagram, determine the symmetry. From the symmetry in the bond polarity determines the molecular is polar or nonpolar, and draw an arrow. Okay, and then you can look at the intermolecular forces. We're going to come back to this later. But let's take a look at some examples. So HCl, take a look at the electronegativity. This is the bond polarity. This is the overall polarity. So this is a polar bond, a polar molecule, and you will have dipole-dipole forces between the two molecules. If you take a look at ammonia, between hydrogen and nitrogen, you will have a bond polarity that looks like this. However, the polarity of the molecule is towards the lone pair, so it is a polar molecule. However, highly electronegative atom with a hydrogen, so it is a hydrogen bond. And here you have a non-polar molecule, less than 0.4, and so non-polar bond, non-polar molecule. So you have to think about London dispersion forces. Okay, so if these two would to interact, polar and a polar molecule, so you will have dipole, right? And if you have these two interact, you will have a dipole-induced dipole. All right, that is it.